Let's take a few minutes now to look at Euler's method, which is a numerical way to find solutions to differential equations. You might recognize the name Euler. You saw him way back in Algebra 2 when we explored the centers of a triangle, and he found that 3 of those centers, the orthocenter, the circumcenter, and the centroid, all lie on a line, and that line is called Euler's line. And you also saw him later in Algebra 2. The constant E, which represents continuous growth, the value 2.718, etc., is actually named after Leonhard Euler. Let's look at this differential equation, dy dx equals x plus y. We have an initial condition, f of 0 is 1. That's like having a point in your slope field. So there is a particular solution, and we're estimating the y value when x is 0.4. Now we could draw the slope field and visualize the solution, but today I want to work numerically using Euler's method. So we're going to do that by making a chart, and it will have 4 columns, and the headings for the columns will be x, y, dy dx, and delta y. And I'll make columns for each of those. And we're going to start at the point 0, 1, and we're going to move through the slope field. And we can choose the increments at which we want to move. And to start with, I want to move in increments of 0.2. So we're going to journey from this point at x equals 0 to our destination, and our change in x will be 0.2 each time. And visually, what's going on here, I'm going to change colors, is that we're starting at this point 0, 1, and we're going to move along a segment in the slope field at horizontal distance of 0.2, and we're going to get to a new location and get a y value. And then we're going to get a new slope at that new location and draw a new segment and go out to a new place. And that will be at x equals 0.4, and the y value there will be the solution, or the approximate solution, to this problem. So let's see if we can do that numerically. At the point 0, 1, our slope is 0 plus 1, which is 1. And when you move along a segment, the change in y is going to be the slope times the change in x. So our slope is 1, our change in x is 0.2, so our change in y is 0.2. So we're now going to take that result, that 0.2, which is our change in y, add it to our original y, and we get a new y value of 1.2. So at this location now, we have a y value of 1.2. And we're just going to repeat the process. We're now going to take our new x and y values, which are 0.2 and 1.2, add them together, and we get 1.4. And we're going to take that slope, multiply by the change in x, and we get 0.28. And we're going to add that result to our old y value, and that will give us 1.48. And I'm going to put a box around that. That is our estimate of f of 0.4. Now you might be thinking to yourself, that's probably not perfect, because in actuality, when you draw the solution curve through a slope field, it has curvature to it. It's not just connected by segments. And you'll notice that the y value that we got is lower than probably the y value on the curve. And that represents the error that we have in using this method. How could we improve the error? Well, rather than use such large increments here of 0.2, we could work in smaller increments, and that would allow us to hug the curve a little closer and reduce our error. And that's what we'll do next. So let's repeat the process that we just went through now, but we're going to use smaller increments. We're going to have the same headings, and you'll always use these headings when you're using Euler's method. And we're going to start at the point 0, 1, but let's increment now by 0.1 rather than 0.2. So our delta x here is equal to 0.1. And we're going to do the same method we just did before. So at the point 0, 1, our slope must be 0 plus 1, which is 1. And now to get our change in y, we take our slope and multiply by our change in x, which is 0.1. And then we're going to take that result and add it to our previous y value. So our new y value is 1.1. And we'll just repeat the process. What you might want to do now is pause the video and see whether you get to the same destination I do, but I'll go ahead and do it now, and you can start the video and take a look at the solution when you're ready. Alright, so at 1.1 for a y value and an x value of 0.1, we add those two together, and we get a slope of 1.2. And when you multiply that by the change in x, we get 0.12. And then we add that to our previous y value, we get 1.22. And then, just like before, we add these x and y values together because that's what the differential equation tells us our slopes are. And we get 1.42. And that times the change in x is 0.142. And we add that to our current y value, and we get 1.362, if I've done my arithmetic correctly. And then we're going to, one more time, add these x and y values, because that's what the differential equation tells us to do. And we get 1.662. And we multiply that by the change in x, so we now have a change in y of 0.1662. And when I add that to my old y value, I get 1.5282, if I've done my math correctly. And I'm going to put a box around that, just like I did before. And that is our new estimate of f of 0.4. You'll notice that it's different from our old one, and it's also going to be more accurate because we've moved in smaller increments. Ideally, our increments that we would work with would be infinitely small, because if they were, we would be moving right along a curve as opposed to using segments to approximate the curve. The last thing I'd like to comment on is the actual solution to this differential equation. It involves techniques that we're not going to learn in AP Calculus, but those techniques are taught in subsequent courses that are devoted exclusively to differential equations. But I do want to share with you the solution. And the solution is f of x equals 2e to the x minus 1. And what you'll notice is that it satisfies this initial condition. When you put 0 in for x here, you indeed get 1 as a result. And also, if you take the derivative, you get 2e to the x minus 1. And what you'll notice is that if you take your y expression and you add an x, you'll get your derivative expression. And that's exactly what the differential equation describes. So, let's now get f of 4 precisely. Or f of 0.4. All we have to do is put 0.4 into our solution. And when you put 0.4 into your solution, we get 2e to the 0.4 minus 0.4 minus 1. And that equals 1.5836. And the decimals go on forever. And this value is higher than our two estimates. But our estimate using increments of 0.1 were closer than our increments of using 0.2.